So this is a circuit, or this is a particular product I wanted to build earlier. It really did not work. I mean, if it works, so it's not efficient and safe to work with. I will tell the reason after in few minutes. So this is the simple BMS board for 2S battery. This is the series configuration casing. So this is the simple must have thing for the 2S casing. It's 2S BMS board. The battery positive negative is here, and the battery middle point is connected to this part, and this is the power pins of the BMS, and these power pins are connected with parallel to this boost converter. It have to focus. So yeah, these power pins are connected in parallel with these four converters. This boost converter's input side is connected parallelly to the BMS power pin, and this boost converter will help to give us any voltage greater than the battery's supply, and battery's nominal supply is 7.4 volts, so we can get 12 volt using this boost converter. Particular number is SX1308 boost converter, which is little bit less powerful than the MT3608. This is the MT3608. This particular module is MT3608, whatever. So yeah, this boost converter will help us to give us 12 volts at very low ampere, around 500 milliampere or 700 at maximum. And then there are two buck converters. I have used two buck converters to get two different voltages below the supply of the battery at the same time. So suppose I have 5 volt for some Arduino Uno project, so I can get 5 volt using this particular buck, where it bucks down. I mean it actually reduces the input voltage which is connected to battery. Suppose the batteries are at around 7 volts around, so I have to cut it down to 5 volt, and this buck converter will cut that 7 volt into 5 volt and supply that 5 volt into the output terminals, which can be used to power Arduino Uno or any Arduino board. And this is the another buck converter which is same parallelly connected to these power pins, and this helps again to buck down or to cut down the voltage at a lower value. Suppose it's 7 volts and I need a 3.3 volt for my let's assume ESP32 projects. ESP32 is a microprocessor which needs 3.3 volt, so I can supply my ESP32 3.3 volt from these terminals. And again, these buck converters are very thin and very small. They are not built for any high ampere loads. A Arduino Uno or ESP32 at maximum load can demand 700 to 800 milliampere, and it can I don't say easily, but can also of course deliver 800 milliampere. They are rated for 1.5, but 1.5 ampere, but I don't believe so. So for around 800 milliampere I am okay with this particular bugs. And this particular bugs output terminals are connected to the BMS pin, not the input. These bugs input terminals are parallelly connected to the power pins, but this particular bugs output terminal is parallelly connected to BMS. The reason is I connected the input terminal. I connected the input terminal into this particular socket so that I can supply 12 volt here, and it will buck down or cut down the voltage at 8.4 volt in this output terminals, which will feed into the BMS board to charge the batteries. So 2S batteries when charging needs 8.4 volt because it's the maximum voltage of 2S battery. 18650 battery I am talking about. These 18650 batteries, yeah, there is the one. Yeah, so this is 18650 18650 lithium ion cells. The length is 65 millimeter or 6.5 centimeter, and the diameter of this particular circle is 1.8 centimeter or 18 millimeter. Hence it calls 18650 form factor. Okay, so this is a 18650 form factor. So this has a nominal voltage of 3.7, and when fully charged each battery have 4.2 volts. So in 2S configuration, they have 8.4 volts. So charge the batteries at 8.4 volts. I need a supply which can give 8.4 volts. But 8.4 volts is a very odd amount. So that I have used this buck converter to convert 12 volt input into 8.4 volt output to charge the batteries. So this particular product looks very fine to everyone, I guess, but the problem is the kickback voltage. It's a phenomenon where any converter, maybe boost, maybe buck, sometimes produces higher voltage value than the supplied one. I mean, if the supply from the BMS is around 7 volt, suppose this is a boost converter, so the supply is 7 volt, the output is 12 volt. Okay, I have set it like that. Supply is 5 volt or 7 volt, supply is 7 volt, and output is 12 volt. So for any moment, something like any problem in the internal circuit or something regarding the this particular inductor which can produce a kickback voltage in this input terminals. So that kickback voltage is nothing but a voltage spike for a very few milliseconds. So that sudden voltage spike can definitely go through this parallel wiring to any other buck converter and can damage them. And similarly, any other buck converter can also has similar kickback voltages, and that can also damage the other ones. So to protect that, we have a concept named ORing. ORing means ORing. So in that ORing, we use Schottky diode or MOSFET based ORing circuit to protect to protect the other components from kickback voltage. It's a very basic idea. We just attach a diode to protect the circuit from bidirectional current. Suppose a voltage spike happens here, this is the positive, this is the negative. So if that happens, so the current will go from this buck to the BMS if this is higher, and at the instant of the kickback, when these input terminals are very high, the current will flow opposite. I mean, from this buck to the BMS instead of the BMS to the buck. So we can easily protect it by using a diode here, which will cut the bidirectional current flow and only allow unidirectional, I mean one directional current flow instead of the bidirectional current flow. So we don't use typical diodes because they have a voltage drop. Voltage drop is a major issue when operating with batteries, because this will this will actually cut the batteries capacity very much. So for that reason, we don't use typical diodes, we use something called Schottky diode. But the problem is that I don't have such low voltage, low knee voltage based Schottky diodes, and I also don't have MOSFETs. I can buy MOSFETs, but they are expensive, and the Schottky diodes are not available in the market currently in the Chandni. So I am stuck with it. So for that reason, I am not using it, because already I have burnt one buck converter and I don't want to burn other ones. So for that reason, and to avoid the kickback voltage phenomenon, I discarded this product or discarded this circuit total contraption and shifted to a very simple design. In this design, I have attached a, again, this is a 18650 battery. Here you can see here, this is a 18650 battery, 3.7 volt. Don't see this capacity. This is a false claim, because a 18650 battery, like in this particular form factor, this particular size, only can hold maximum around 3600 milliampere or 3.6 ampere hour capacity. This is claiming 7500 milliampere hour, which is completely false, because theoretically it can only hold 3600 milliampere hour. So although it's a Chinese brand, you can see the Chinese kanjis are here. So this is a totally false claim, whatever. So this kind of batteries only supply 3.7 nominal voltage. So I need a 5 volt supply for the digital work of my electronics. In the digital work, we need 5 volt supply for different logic ICs, such as the TTL 74 series or CMOS based 74 series, such as 74HC series. So there are multiple IC series which needs 5 volt, and they don't actually need high ampere, because they have such kind of architecture inside them that their input impedance is very high. For that reason, they don't actually draw a lot of current, and they are very power efficient. So this kind of buck converters are very useful in that particular situation, because this particular buck converter, sorry, this is a boost converter. So this particular boost converter, model name MT3608, so this particular boost converter is boosting the 3.7 volt supply of a single 18650 lithium ion battery. So it, as it is a single lithium ion battery, the supply is 3.7 volt nominal, and it actually boosts that supply into 5 volt output. So actually these are the input pins I have configured like that. These are the input pins, V in minus, V in plus. So V in plus is connected to the output of the TP-Link module via a switch, and the V in minus is connected to the output minus of the TP-Link module via wire directly. So this switch controls the supply of the power, power supply of this particular buck converter. Yeah, so this particular buck converter is actually getting 3.7 nominal voltage in these two terminals via this TP4056 module, and it boosts that 3.7 volt into 5 volt here. So this is a adjustable boost converter. Here is the uh, port. You can see this is a 3296 multi-ton precise port, precision port. So this precision port can be adjusted, the port can be adjusted to get any output voltage from the input voltage to 16 volts, which is more than we need most of the times, because this particular boost converter does not has the power or the capability to give higher currents. So for that reason, we use these boost converters where the current demand is very low, such as my digital work or digital IC construction or circuit construction using digital ICs. So yeah, that was the whole boost converter. These are the input pins, and these two are output pins, which has been connected to these two wires, positive negative, positive negative. Why I have two wires? Because any breadboard has two power lines, and to connect the power lines simultaneously, I have used total two pairs of red and black wires. So that's all. And here is the everyone's favorite for TP4056 module. So this has total two ICs. This particular variant has two ICs. This is TP4056, which is the main IC, which actually protects, sorry, which actually charges and cuts the supply of the charging when battery reached 4.2 volts. So this ICs, this module, we use this particular module to protect our battery when charging. So suppose the battery is at around 3 volt, yeah. So this particular IC will see that the battery has 3 volt. So we connect the supply here, 5 volt supply here, using a USB. 5 volt feeds in, and it converts that 5 volt into any desired voltage, and then charge the battery. And when the battery reach 4.2 volts, so when the battery reach 4.2 volts, it actually cuts off the charging to protect the battery from any overcharging or any kind of accident because of the overcharging. And there is in the bottom a dual MOSFET. There is two MOSFETs in this particular black box, and it actually detects how much current is flowing. It's bidirectional. It can detect how much current is flowing into the battery and flowing out of the battery to take decision based on that. So if the battery is almost charged, then it will say that to limit, it will actually help to limit the current, because when the battery is almost charged at around 4.1 volts, the charging should be slower to protect the battery's life. Or when the battery is discharging, this particular IC is looking for how much current is flowing out of the battery. If the current is very high, then it will say that to reduce the current limit, it will say to it will detect that, and this is the particular IC which will set the current limit. So this IC, this dual MOSFET actually detects how much current flowing into and out of the battery. Okay, that's simple. And this is a particular IC, model name most probably DW10, and that DW10 IC, they need a input that how much current is flowing into the battery and out of the battery, and they take decision based on that. Is the current flowing out of the battery too much? It is, if it is too much, then this particular IC will give particular voltage to the MOSFET to control the current. And if the charging is almost done at around 4.1 volt, this IC will tell the MOSFET to slow down the charge to protect the battery. So this is a so this module has two parts. The upper part is the charging and only charging part. This 4056 module, 4056 IC, this particular part is for charging, and this particular lower part, which is already connected to whole module. Okay, so this particular lower part is for overcurrent protection, it's for overcurrent protection, or you can say over discharge protection, because when the battery goes below 2.7 volt or 2.6 volt, then this particular IC, again DW10, detects that and say to the MOSFET to disconnect the battery from the output pins, and it will help the battery from going to the discharge state. So in deep discharge state, the battery gets almost completely discharged. For that reason, it is hard to recharge them. So for that reason, this IC is here, and it will detect that if the batteries, this particular battery's voltage drops below 2.6 volt, it will set the MOSFET, this particular MOSFET pair, to cut off the voltage supply to protect the IC from a deep discharge state. Okay, everything is fine. So two modules are there. This is TP4056 for charging and overcurrent protection, and auto cut feature, for the auto cut feature when battery gets fully discharged or at around 2.6 volts. And this is the boost converter to convert the output of the module, which is 3.7 volt, into 5 volt output for my digital work. Okay, so again, this is the trim port here, which can be used to get any other voltage, but remember that the MT3608 has 2 ampere max pulse current rating, and at continuous current it can deliver most probably 1 to 1.5 amps at max to max possible scenario with a proper heat sink. If you don't use heat sink here in this particular IC, small IC, in this particular small IC, if you don't use heatsink here, then it can deliver max to max 1 ampere only. 2 ampere rating is for a pulse current. Pulse current is different than a continuous current. Okay, so this is the total module. So let's demonstrate it. I have talked a lot of words in this whole time, so let's demonstrate it. So connect it here. uh, yeah, connected here, connected, turn on the supply and measure. So as you can see, I guess, so I have connected the supply and turned on the switch. The 1 is on and 0 is off, so it's in one side, so it's currently on, the module is currently on. So measure the potential difference between the power rails. So this is the positive power rail, this is the negative power rail, and you can see the so this is the negative power rail where I inserted the ground pin of the multimeter, and in the positive power rail I have inserted the red wire of the positive wire of the multimeter, and the multimeter is reading 5.05 volts. So I have adjusted it at 5.05 because if few milliamps of current is drawing, then it will drop down. So as you guys can see, it is fluctuating for some reason, I don't know actual reason. Yeah, so if few milliamps are drawing in this particular power rails, it will drop few volts, very few millivolts. So for that reason I have set it up to 5.05 volts. So this is the potential difference of this particular this particular power rail. Let's measure the potential difference of this particular power rail. So remove that and insert into this positive rail, remove that, insert into this negative ground rail. So yeah, if it's also not fully inserted, you can get the reading. So the reading is again 5.05 volts. So this particular power rail also has the potential difference of 5.05 volts, and that's what I needed. So yeah, let's start it off the multimeter and everything. Let's remove them. Turn off the power, remove the jumper wires. So again, this product, I mean this particular contraption, I built just to boost this 3.3 volt into 5 volt to be able to use it for digital works. I mean digital IC related 74 series IC related works. And I have it attached a 4056 module to charge the battery also. So this is for charging, this is for power up, I mean boosting the voltage from 3.7 to 5 volt. And this is all. There is the switch to turn and off the power. And yeah, it total cost me around, it's 50 rupees boost converter, 20 rupees, 20 to 25 rupees I guess the power charging module. Casing is 20 rupees and the battery is 90 rupees. This is a premium battery. So at total it around cost me 200 something rupees. And but it's very handy for me particular, because it's very portable na. So for that portability it's very handy for such people who needs 5 volt supply on the go without any higher current demand. Again, this particular thing can't supply more than 1 amp, so remember that.